Hello everyone, welcome to Chem76A. Today we will begin chapter number 6. In previous chapter we learned about alkenes and we discussed what are alkenes, their nomenclature and their properties. In this chapter we will explore reactions of alkenes and one reaction which we will focus on, and that reaction is addition reaction. Just like alkenes are also known as hydrocarbons because they are made up of hydrogen and carbon. As we learned in chapter number 2, the chemical reactivity of alkanes is quite low. They show very few chemical reactions. In contrast to alkenes do show a wide variety of chemical reactions. This uh, increased reactivity of alkenes is because of the presence of carbon-carbon double bond. So all alkenes are characterized by a presence of a carbon-carbon double bond, and we learned in previous chapter that one of this double bond is a sigma bond, the other bond is a pi bond which is made up of sideways overlap of p orbital. The bond energy of this pi bond is only 264 kilojoules per mole, and this bond energy is not that high. So what it means is that pi bond can be broken down easily, and because of this alkenes show a variety of reactions in which the pi bond breaks up, and after breaking the pi bond, these carbons will have a place where another group or element can be added. So these kind of reactions are known as addition reaction because two new groups or atoms will be added across the double bond. The double bond, of course, is not there anymore. So these kind of reactions are known as addition reactions. So because pi bonds can be easily broken down, so alkenes show a wide variety of addition reactions. Some of the common addition reactions of alkenes are listed in this table. Some addition reactions have special names that indicate the identity of the groups that were added. For example, if we add water across the carbon-carbon double bond, we can consider water as HOH. So it means one side will get hydrogen, the other side will get OH. So the name of this addition is hydration. Similarly, if we add hydrochloric acid or hydrogen chloride across the double bond, then the reaction is known as hydrochlorination, or in general hydrohalogenation if you add Hi or HBr. Similarly, it will be known as hydrobromination or hydroiodination. Addition of any halogen across the double bond is known as halogenation. In halogenation, mostly the reaction is carried out by bromine or iodine. Bromine and chlorine. Fluorine and iodine are not favorable in this reaction. In presence of water and halogen, the reaction is known as halohydrin formation. In this reaction, one side of the double bond will get a halogen and the other side will get the OH group. So therefore, this kind of reaction is known as halohydrin formation. Some of these reactions are treated separately under oxidation and reduction sections. For example, these are examples of oxidation reaction, and then this is example of reduction. However, in general, they are still known as addition reaction because they are formally additions. As you can see in oxymercuration, one side gets added with OH group and the other side gets added with the mercury oxyacetate, and so on. So although these reactions will be covered under oxidation and reduction section when we study their mechanisms in detail, but formally they are still known as addition reactions. The concept of reaction mechanism and reaction coordinate diagram was introduced in chapter number 4. Chapter 4 dealt with acid-base chemistry, which involves the transfer of proton from one chemical entity to another occurring in single step. Although in organic chemistry, many reactions do occur in single step, but however, many more involve two or more steps. A reaction mechanism in those reactions describe how the reaction occurs. A reaction mechanism explains which bonds are broken and which new ones are formed. It also explains the order of relative rates of various bond breaking and bond forming steps. If the reaction takes place in a solution, reaction mechanism will explain the role of solvent. And if there is any catalyst, reaction mechanism will also explain the role of that catalyst. The reaction mechanism explains the position of all atoms and energy of the entire system during the reaction. Before we learn how to draw a reaction mechanism, it is extremely important to explore the factors that cause reactions to occur. Many of these factors are related to thermodynamics of the reaction as well as the energy diagram. So in this section, we will learn about important concepts of thermodynamics as well as energy diagram. More importantly, we will focus on the skills necessary to draw and interpret the individual state of a reaction. Understanding of these concepts will help us to develop the core concepts and critical skills necessary for understanding chemical reactivity. So let's start with one of the most important thermodynamic equations. So this is called Gibbs free energy change equation. Gibbs free energy change equation is a thermodynamic function which relates enthalpy, entropy, and temperature of a system. And this equation is described here. We'll come back to this equation in a minute. Let's first understand what is the importance of this equation. Now, free energy change, that is delta G value, can be used to predict if a reaction will be spontaneous or will not be spontaneous. In other words, delta G can be used to determine if a reaction will take place or will not take place. Those reactions in which the change in free energy, that is the delta G value, is negative, those reactions favor the formation of products. And in case the reaction has a delta G value positive, these reactions favor reactants. So favor reactants means that the reaction will not take place. Okay. Now the reactions in which the Gibbs free energy of product is lower than that of the reactants, in that case, the position of equilibrium will favor products. How? Remember, delta G is the free energy of product minus free energy of reactant. If the product free energy is lower and the reactant free energy is higher, then delta G value will be negative. Okay. So in the case where the product free energy is lower than that of reactant, the value of delta G will be negative and the reaction will favor products. These kind of reactions are known as exergonic reactions. So if I have to define, I can define exergonic reactions are those reactions in which the change in free energy is negative. What's the meaning of negative free energy? Negative free energy means that some of the energy is liberated or generated out or released. On the other hand, the reactions in which the Gibbs free energy of product is higher than that of reactant. In these cases, remember delta G is equals to G product minus G reactant. So now product energy is higher and reactant energy is lower. So therefore, overall this value will be positive. In these cases, delta G value will come out to be positives and these reactions favor the starting material. The meaning of favoring starting material means that the reaction will not go towards the product side, hence the reaction will not take place. These kind of reactions are known as endergonic reactions. So if I have to define what are endergonic reactions, now endergonic reactions are those reactions in which free energy is absorbed or there is a positive free energy, or in other words, the system free energy increases. So these reactions are not favored. As we learn that the change in free energy of a reaction can be used to determine if a reaction favors the formation of products or stay as reactants. So if delta G is negative, it will favor the formation of product. If delta G is positive, it will not favor the formation of products. Now the problem is that, as we defined earlier, that delta G is equals to a difference in the absolute values of free energy of product minus free energy of reactants. However, it is impossible to calculate the absolute values of free energy of reactants and products. So these two values cannot be calculated. Then how can we calculate the change in free energy if we don't know the absolute values? That's where the relationship between free energy, enthalpy, and entropy comes in handy. We know that the change in free energy of a reaction is equals to the change in enthalpy of reaction minus T delta S, where delta S is the change in entropy of that particular reaction. This not represent that the reaction was carried out at standard states. From this equation, we can see that free energy change depends on the enthalpy change as well as it depends on the entropy change. Now, if a reaction is exothermic, so exothermic reaction means the enthalpy value will be negative. Okay, and if a reaction is such that there is increase in entropy, so increase in entropy means, remember, entropy is a measure of randomness. Increase in entropy means there is more randomness in the system. So in that case, delta S will be positive. So if delta S is positive, so negative T delta S will remain negative value. Okay. So in other words, this value is negative, this value is also negative, so overall value will be again negative. It means delta G will be negative in that reaction. So therefore we can say the reactions in which the enthalpy is negative and entropy is positive, those reactions will favor the formation of products. That's one possibility. Okay. All right. So let's look at another possibility. So let me rephrase it again. So those reactions in which the enthalpy is always negative and entropy of the reaction is always positive, those reactions will end up giving delta G value to be negative, and hence those reactions will always favor formation of product. So delta G less than 0 position favors the formation of product. Okay, so let's take a look at another example. Now imagine if we have a reaction in which the enthalpy of the system is positive. So positive means reaction is endothermic. So endothermic reaction, so it means delta H is positive. Okay, negative, and delta S is such that the reaction is more ordered. After the reaction, there is more symmetry or more order. If there is more symmetry or more order in the reaction, then the delta S value is negative. Remember, more randomness means increase in entropy. Less randomness means more order, means decrease in entropy. So if it's more random after the reaction, then delta S value will be positive. If the reaction leads to more ordered structure or less degree of freedom, then delta S will be negative. So in that case, T minus some negative value. Okay, so this is positive. So negative times negative, the value will also be positive. Okay, so therefore delta G in that case will always be positive. So these are the systems or these are the reactions in which delta G will always be positive. So always positive means that the reaction favors uh, equilibrium favors the reactants. So when it means when delta H is positive, delta S is negative. So these are the reactions in which delta G will always come out to be positive, and the reaction equilibrium will always favors reactant. So it means that the products will not form. So these are two extreme cases. Now there is one or two middle cases also. Let's discuss those two also. So imagine if a reaction is exothermic. Reaction is exothermic. So exothermic means that the delta H value is negative. That's good, right? Because we want delta G to be negative. But however, the reaction is such that it is leading to more order. So more order means delta S is also negative. Okay, so now it's a tricky situation. Okay. So why it's tricky? Because one of the value delta H is good for us because we want the overall value to be negative. But look at the other one. So this negative times this negative. So now this value will be some positive value. So T times some positive value. Now in this case, if this overall value is large, okay, or larger than delta H value, then delta G will become positive. Okay. Now, how can it be larger than delta H? If T value is extremely large. If T is extremely large number multiplied by some positive value will make this entire number large. Entire number large means it will be bigger than the delta H value. So hence the overall delta G will become positive. So it becomes unfavorable, right? So that means that the reactions in which delta H is negative, but delta H delta S is also negative, then it depends at temperature. At low temperature, it will be small enough, then the delta H value will be more dominant factor and delta G will be negative, and in that case it will favor the products. Okay, only a lower temperature. But if we increase the temperature, then in that case this overall value of entropy function will increase, and this will be large enough to overcome the negative value of delta S function. So entropy will win in that case, and delta G will become positive, and the reaction will become unfavorable towards product. And then the fourth case is the one in which delta H is positive but delta S is negative. In that case, reaction will be spontaneous, or it will favor products if the temperature value is large, but it will favor reactants if the temperature value is small. So think about it. So do all kind of manipulation. Just think about the values, and you will be able to summarize it as shown in this table. The change in enthalpy is the difference in total bond energies between reactants and products. In a chemical reaction, some old bonds are broken and new bonds will form. The bond breaking step of a chemical reaction requires absorption of energy because we need energy to break any bond. For example, if we want to break this bond, this process will be an endothermic process because energy is absorbed. So therefore, we can say bond breaking process is endothermic process. So if bond breaking is endothermic, then the opposite of bond breaking, which would be bond making, will be exothermic. This is because of law of conservation of energy. If energy is released in a process, then the energy will be absorbed in reverse of that process, or vice versa. So therefore we can say that the bond making process is exothermic, or energy is released. Now heat of reaction is the difference in the enthalpies between reactants and products. So if in a process we need less energy to break the bond, but overall it releases more energy when it makes new bond, then that process will have a net release in energy. Therefore, these kind of reactions are known as exothermic reaction. Let's take an example of alkene addition reaction, because that's what we're going to study here in this chapter. So in alkene addition reaction, the end product will be addition of a molecule across the double bond. So in this process, let's identify which bonds needs to be broken. So first, a pi bond breaks and the sigma bond between A and B breaks. So two bonds will break. On the other hand, the new bonds which will form are so both of these bonds are sigma bonds. As we know that pi bond is weaker than sigma bond, so when we break it, so we break one weak and one strong bond. So these bonds needs to be broken down and they will require energy. So energy will go in. But both bonds are strong when they are formed. So it means in this case, in this process, less energy is needed to break the bond because one of the bond is weak, the other one is strong, but more energy will come out. So less goes in, more comes out. So therefore, addition reaction of alkenes are exothermic because less energy goes in and more energy comes out. Similarly, there are many processes in which more energy is needed to break the bonds and less comes out. In those cases, a net overall absorption of energy will take place, or absorption of heat will take place. These kind of reactions are known as endothermic reactions. The change in energy of a reaction can be best represented with the help of energy diagrams. Now, energy diagrams are a graph in which a curve represents the change in energy of the system as the reaction proceeds. An example of an energy diagram is shown here. In these diagrams, the progress of the reaction, which is known as reaction coordinate, is plotted along the x-axis, and energy is plotted along the y-axis. This energy diagram represents a chemical reaction between the reactants A-B and the other reactant is C, and the products are AC and B. So in other words, the bond between A and B breaks and a new bond between A and C is created. So this is a one-step process, and the progress of this reaction is shown with the help of this energy diagram. As we can see on the left hand side, the starting material, which are reactants, have some energy. So this is the amount of energy, potential energy stored in these two reactants. Now, when a chemical reaction takes place, because all these molecules are moving randomly in space, they collide with each other. Some of the collisions have less energy because the kinetic energy may be low, but some collisions will have a high energy. So as the reaction proceeds, most of the molecules will collide with each other, but some of the molecules will collide with such a high kinetic energy that this collision will lead to the formation of a transition state. Now, transition state is an intermediate state, or it's an activated state in which the bond between A and B is uh, almost ready to break. Now, because we need energy to break that bond, so therefore that energy is supplied by the collision, by that high velocity collision. So some collisions will have enough energy to provide this much energy which is needed to break this bond, and when that happens, it crosses this barrier. So this barrier is known as activation energy. So activation energy is the amount of energy required to break the bond between the reactants. Once that happens, then new bond between A and C will form, and once this bond forms, this process of bond formation, as we know, is endothermic. Energy is released, so the overall energy of this complex will go down and we get product. Now, if the products are at lower energy than the reactant, the total amount of energy absorbed was this much and the total amount of energy released was this much. So there will be a net release in energy. So the difference between the energy of the reactants and energy of the product is known as heat of reaction, or heat of reaction is also known as enthalpy of reaction. It's same as delta H. The unstable state which is formed during the course of this reaction is known as the transition state. It is the height of the reaction progress curve. So it also represents the maximum amount of energy in that reaction curve. The activation energy is the difference in Gibbs energy between reactants and the transition state, or in other words, the activation energy is the amount of energy required to cross that transition state barrier. activation energy is denoted by delta G. If delta G is large, very few collisions will be capable enough to cross that barrier, because large activation energy means that the collisions between the reactant has to be at relatively high kinetic energy, because we need high energies required to cross that barrier. But if delta G is small, so for example, if the barrier is large, then very few collisions will be capable enough to cross this barrier. But in some other reaction, if the activation barrier is small, then low delta G is required, so most of the collisions will be effective to cross that barrier. So low delta G will give reaction rates which are very fast, and high delta G will result in reactions with very low rate of reaction. In a reaction that occurs in two or more steps, each step has its own transition state and activation energy, as shown in this diagram. In these reactions, a reactive intermediate will form, and it corresponds to an energy minimum between two transition states. Although this reaction intermediate is stable as compared to transition state, however, the energy of this intermediate is considerably larger than both reactants and products. So therefore, reaction intermediate are extremely unstable species. So they exist only for a small fraction of a time. Most of these reaction intermediates are extremely reactive, and uh, they will break into, or they will transform into product in very small amount of time, so therefore they cannot be isolated. However, some reaction intermediates have considerably high life time, and they can be isolated and analyzed. We encounter three types of reaction intermediates in most organic reactions. In first, we will have a species in which a carbon atom carries a positive charge. In this species, uh, the carbon atom which carries a positive charge has only 6 valence electrons, so hence it is quite unstable, and these kind of intermediates are known as carbocations. Second type of intermediates are those in which we will have a carbon atom and it will have a single unpaired electron. These kinds of intermediates are electrically neutral and they are free radicals, and carbon atom which carries the radical uh, electron has only 7 electrons around it. So therefore this kind of intermediate is known as uh, carbon radical, or it's just simply called radical. And the third kind of intermediate is the one in which the carbon atom has a negative charge, and the octet of this carbon is complete, but because carbon does not have high electronegativity value, so therefore it's also unstable. These kind of intermediates are known as carbanion. In alkene addition reactions, we will only encounter carbocations. So in this chapter, we will only study carbocations. However, we will see carbanion as well as carbon free radical in other chapters. The process of developing a reaction mechanism involves several steps. In the beginning, chemists propose several mechanisms, or they propose several sets of steps that might account for overall chemical transformation. Next, chemists test each proposed mechanism by designing and carrying out experiments that provide experimental observation, which allows them to exclude those mechanisms that are not consistent with the facts. A mechanism becomes established by excluding reasonable alternatives and by showing that it is consistent with every test that can be devised. This, of course, does not mean that generally accepted mechanism is a completely accurate description of the chemical event. It only means that it is the best mechanisms we have been able to devise. It's important to keep in mind that as new experimental evidence is obtained, it may be necessary to modify a generally accepted mechanism. So at this point, we may ask that why chemists go to such trouble of establishing a reaction mechanism, and why we must spend time to learn about them. So one reason is very practical. So that reason is that mechanisms provide a framework within which to organize a great deal of descriptive chemistry. For example, with insight into how reagents add to a particular alkene, it is possible to generalize and then to predict how the same reagents might add to another alkene. The second reason lies in the intellectual satisfaction derived from constructing models that accurately reflect the behavior of uh, a chemical system. So for a creative scientist, a mechanism is a tool to be used in the search of new information and new understanding. A mechanism consistent with all that is known about a reaction can be used to make prediction about chemical interactions yet unexplored, and experiments can be designed to test those predictions. The ability to write an organic reaction mechanism is key to student success in organic chemistry classes. Organic chemists use a technique called electron pushing to write any reaction mechanism. Electron pushing is also known as arrow pushing, and it is used to depict the flow of electrons during a chemical reaction. In electron pushing, we must obey certain rules. So let's go over those rules. So rule number one, arrows are used to indicate the movement of electrons. It is extremely important to note that uh, in reaction mechanisms, we do not show the movement of atoms. We only show the movement of electrons. A curved double-sided arrowhead is used to show the movement of two electrons. For example, this lone pair of electrons are moving to become a double bond here, so therefore we are using a double-headed arrow. On the other hand, a single-sided arrowhead is used to show movement of one electron. For example, if a carbon-carbon double bond uh, or an alkene is undergoes a process called hemolysis. In hemolysis, normally takes place in presence of light. The pi bond breaks evenly. Even breaking means one of the electron will go to one side and the other electron go to the other side. So for example, if hemolysis takes place on this alkene, so we show a single-headed arrow, and these single-headed arrows will represent the movement of a single electron. But a double-headed arrow is used to show the movement of two electrons. For example, this pi bond is moving, and and a non-bonding lone pair of electron is moving as shown in these two mechanisms. When writing any uh, curved arrows or during arrow pushing, we must keep in mind that in case of resonance, the atoms do not move between contributing structures. And secondly, these electrons are not actually moving. Although it looks like the electrons are moving as shown here, it looks like this double bond moved from this CO bond to now this CO bond. But it's just a way we represent the resonance structure. The actual molecule is the hybrid of these two contributing structures. Or in other words, the actual molecule is somewhere in the middle of these two molecules as shown by this computer simulated model. As we can see, the red part represents the electron density. So in resonance structures, we can see the electron density is either on this oxygen atom or on this oxygen atom, right? But however, if we look at the actual model, we can see the red part is evenly distributed. So this is only possible when the actual structure has a kind of a hybrid structure of both, where the electron is distributed on both of these oxygens. Rule number 2 is that arrows are never used to indicate the movement of atoms. For example, if uh, we write the reaction mechanism step in which a carboxylic acid is transferring a proton to a base, so if we write the reaction mechanism such as this step, although it looks correct, hydrogen moved from carboxylic acid to the oxygen of OH group, but it is wrong because arrows are never used to indicate the movement of atoms. So this step is incorrect. The correct step is that we use curved arrows to show the movement of electrons, not atoms. So correct mechanism would be that the OH group donates its electron to make a bond with hydrogen, and the sigma bonded electron between oxygen and hydrogen moves to the oxygen of carboxylic acid. So this is correct. The third rule states that our arrows always start at an electron source and they always end at an electron sink. An electron source generally is a pi bond or a lone pair of electrons on an atom of relatively high electron density. Sometimes it may be a sigma bond electrons which must break during a reaction. On the other hand, electron sink is an atom on a molecule or an ion that can accept new bond or a new lone pair of electrons. Rule number 4 states that bond breaking will occur to avoid overfilling valence uh, electrons on an atom serving as an electron sink. So it means that atoms cannot have more than octet or duet in case of hydrogen when electrons are moved. For example, in this example shown here, when we show the movement of lone pair from oxygen to hydrogen, we must show this electron also, movement of the sigma bonded electron also. The reason is, if we do not show it, then hydrogen will have expanded duet, so which would be incorrect. So sigma bond will break in order to uh, avoid that condition. A broader terminology is applied to the very common cases of reactions in which new sigma bonds form between electron-rich and electron-poor regions of molecules. Electron-rich region is known as electron source, and electron source is a molecule that have extra electrons in it. Those extra electrons may be present in form of pi electrons or sigma electrons, but electron source always have extra electrons, so it is electron rich region. Now electron source or electron rich regions are known as nucleophiles. Nucleophile means nucleus loving. So why would it be nucleus loving? Because it has extra electrons. So extra electron means more negative charge on it. So therefore it seeks the nucleus to, nucleus is positive. So the nucleophiles, they seek positive nucleus to neutralize the extra negative charge. So electron sources are also known as nucleophiles. For example, OH negative ion is a nucleophile because it has extra negative charge, and of course it's also electron source. There are many other examples of nucleophiles. Some nucleophiles are strong, some are weak. The meaning of strong nucleophile is that it has too many electrons, or electron density is too high on it, so that it really wants to donate that electron density. On the other hand, electron sink is an area or a molecule which lacks electrons, and that's where the electron source can donate the electron density. So electron sinks are also known as electrophiles, which means they love electrons, so electron loving. Why they love electrons? Because they lack electrons. Uh, So electrophiles are molecules with relatively electron poor atoms that serve as a sink for arrow pushing. So if you remember, Lewis acids are also species which absorb electron pair. So Lewis acids are analogous to electron sinks. So therefore BH3 is a good example for being an electrophile. So when we draw the arrow pushing, we always show the movement of electron from electron source to electron sink. In other words, we always show the movement of electron from nucleophile to electrophile. In order to master organic chemistry, it is extremely important to understand a reaction mechanism. I would like to point out here that memorization of a reaction mechanism rarely works. Although the mechanisms which we will encounter throughout this course may seem entirely different, but they are related to each other in many fundamental ways. In fact, almost all organic reaction mechanisms are composed of these three classical steps. So in almost all reaction mechanisms, we will see redistribution of pi bonds and or lone pairs. We'll see formation of new sigma bonds from a lone pair or a pi bond, and we will also see breaking a sigma bond to give a new lone pair or a pi bond. So the point is, although mechanisms look different from each other, they're all made up of these three fundamental steps. Our job here is to identify these steps and identify various patterns of electron movement. As long as we can understand and master these patterns of electron movement, we can come up or we can write any reaction mechanism. Fortunately, uh, we don't see a lot of reaction movement patterns. There are only 4 patterns. So let's go over these patterns. So pattern 1 is the movement of electrons such that a new bond is formed between a nucleophile and an electron file. Or in other words, in this pattern, a sigma bond will be generated between electron source and a sink. I also call this pattern as a nuke attack because it sounds cool. What it means is that it is a attack by a nucleophile. So for example, the water here in this reaction is a nucleophile because it has extra lone pair. So it attacks, as you can see, the electron source. So this electron source is an electrophile because it lacks electron. So I call this pattern a nuke attack. All organic reactions normally start with this pattern. So first step of most of the reaction mechanisms will be a nuke attack. Pattern 2 is a breaking of a sigma bond so that relative stable molecules or ions are created. I call this as a loss of leaving group. So in this pattern, a leaving group will leave a molecule or an intermediate to form relatively stable molecule or anion. For example, in this case, bromide leaves this alkyl halide. The reason is bromide ion is a relatively stable anion because it's a large, its electronegativity is relatively high, so it can hold this extra negative charge. So it's a relatively stable halogen ion. So this pattern is I call this pattern loss of leaving group. Pattern 3 involves a transfer of proton, and it is observed whenever there is a strong acid or a molecule which has a strongly basic functional group. So I call this pattern as a proton transfer step. As the name suggests, in this pattern, proton will be transferred. As shown here, a proton is being transferred from hydronium ion, which is strongly acidic, to ethyl acetate. So fourth pattern is take a proton away. It is similar to proton transfer. We use this pattern when a molecule has a strongly acidic proton or if there is a strong base present, but it looks similar to proton transfer.